notes, we are going to be learning about currents, waves, and tides. You should have been able to either print out the PDF guided notes worksheet that was on your checklist, or you should be able to be prepared to write everything out on a loose sheet of paper as we learn more about these characteristics. First, we're going to talk about ocean currents. So the water in the ocean is constantly moving. We know this. You can't even look at a bay like the Chesapeake Bay and not see some movement. Now, on the surface, we see water moving in the form of waves, but below the ocean surface, this water molecules move as great currents. Ocean currents are moving streams of water within the ocean, and there are two types. Now, surface currents and deep currents, it's pretty much where are they located. If it's, again, on or near the surface, it's going to be a surface current. If it's below, it's going to be, again, deep. Now, let's talk a little bit more about surface currents. There are three factors that control surface currents. These are air currents, wind, the Earth's rotation, which we'll get a little bit more into that, and then, of course, the location of continents, because water's got to go around them. Surface currents travel much faster, though, than deep ocean currents. Now, let's look at this picture. This is, again, sort of the direction of ocean surface currents in the world. We get the red and the blue arrows based off of the temperature. You'll notice that one of the reasons why the East Coast is a whole lot more humid than the West Coast is what type of water. Is it warm or cold that's going up against the coastline? The East Coast gets that warm air and the warm water coming from the equator, whereas the West Coast gets it from the Arctic, where it's a lot cooler, which is why, again, that's the type of temperature you also have on the West Coast. Now, deep currents. This is the stuff that's, again, deep in the water. Water density is one of those things that, again, help with deep currents. Temperature, salinity, all of these can, again, change how water moves. Now, we know that cold water is more dense, and it sinks and it moves. Warm water is less dense, and so it rises up. So even within deep currents, you have this sort of cycle of warm and cold water that is creating movement. We can't talk about current unless we also talk about wind. So first of all, we got to talk about global wind belts. So this again is the major factor behind when we said air movement as one of the causes behind surface currents. Now, trade winds are the winds that are located just north and south of the equator. You have, again, the northeastern trade winds and the southeastern trade winds that are, again, on those. And you'll see that they actually go in different directions. One going counterclockwise, the other one going clockwise, and this is due to the rotation of the Earth. Now, westerlies are, again, located in the middle latitudes, not at the very tops, but the middle latitudes, and you also have these Hadley cells and other types of cells where these sort of wind things is sort of almost recycled and cycled through that. So you can see on the sort of cycle arrows that you see on the the right side of the picture. Now the Coriolis effect. The Coriolis effect, you can hear both different ways. That's the bending of the Earth's winds due to the ocean currents due to the Earth's rotation. So because the Earth is rotating, things in the northern hemisphere deflect to the right. In other words, they go clockwise. But things in the southern hemisphere, they go counterclockwise. They deflect to the left. And this is even going to affect hurricanes and tropical storms. The way that they rotate is based off of this. Now, deep currents. As you can see, we talked about how even warm and cold water is going to create movement just because We know warm rises, cold sinks because things are more dense or heavier. Now with that, you also get these sort of deep currents that go through, again, the ocean. If you sort of remember in Finding Nemo, this is the currents that the turtles, the sea turtles, were sort of riding along. Now with waves, waves are just rhythmic movement that carry energy through matter or space. Now, we also have ocean waves, but think about earthquakes. We had P waves, and we had S waves, we had body waves, we had surface waves, and that was just with energy with earthquakes. But we also have waves in the ocean because waves can travel through water. Now, how are these, again, waves created? Majorly through wind. We also have some for gravitational force from the moon and the sun, which we'll talk about, which we are calling about tides. But earthquakes can create humongous waves, which we call tsunamis. Now, part of a wave, you should have this diagram in your notes. If you don't have the diagram, if you're handwriting it, you do need to draw it out. But you have 4 different parts of the wave. You have a crest, a trough, the wave height, and the wave length. So the crest obviously is the crest of something, that is the top of something. The trough, think of like a feeding trough, is something that dips down below. That would be the wave trough. Now wave height is the vertical distance between the crest and the trough. Okay, and wave length is the horizontal distance between the 2 crests and the 2 troughs. Wave movement. So this can sometimes be difficult to understand. When a wave passes through the ocean, water molecules are just moving up and down. And we see the water molecules, I tried to sort of, the picture that I put here, again, it's showing just this movement of up and down movement for waves. The only time we actually get water moving backwards and forwards is when a wave breaks. So when a wave breaks against the shore, the crest outruns the trough and the crest collapses, and we call this a breaker. And this is really the only case in which water actually moves forward and backwards. Otherwise, water molecules are just moving up and down, and the energy is moving forwards. Now, tides. Tides, a tide is a periodic rise and fall of the sea level under the gravitational pull of the sun and moon. You can have high tide, low tide, and then the tidal range is actually the difference between these two. Now, look at the pictures that I have, the 2 GIFs that I have. You can see the difference between high and low. The high tide happens twice a day, the low tide happens twice a day. You can also see a slower sort of time with tide height in the secondary picture that is to the right, where again, if you look very closely, you're going to see the low tide ebbing out and then the high tide flooding in. Now, there are some differences between high and low, and even the high tide and low tide of places around the world. It's not the same. And we know that there's 2 high tides and 2 low tides. They happen approximately every 24 hours and 50 minutes a day. So you have about 12 hours and 25 minutes between the 2 high tides, and you have the same amount between the 2 low tides. Now, the difference between the 2 is going to be local geography, what the coastline looks like. That will depend on how high the tide rises or how far it goes out. The topography of the ocean floor, even though you don't see it, it definitely plays a part in, again, what the difference in the tide and how far it recedes and goes back up. And then, of course, the depth of the water. Now, if you look at this picture again, I'm going to replay it so that we can see it. This is the Bay of Fundy. Has one of the highest, again, tidal ranges in the world. Look at how different high and low tide is. It's crazy. Now let's talk about spring and neap tides. These happen twice each during a lunar month. We say lunar month because, as you know, the full moon and the new moon don't always happen every single same time every regular month. but they do happen on a lunar cycle, because remember that the moon is rotating around the Earth too. Now, we get spring tides when the sun, Earth, and moon are in a straight line, whether the moon is in between the sun and the Earth, or whether the Earth is in between the sun and the moon. This is going to give us spring or neap tides. This is because the forces, the gravitational forces of the sun and the moon are pulling the gravitational forces of the Earth. With neap tides, these are quarter moons, either the first or third quarter. The sun and moon are perpendicular. Spring tides have the strongest tides. They also have the highest high tide, and neap tides have the weakest tides or the highest low tide. I'm going to go back to this and explain just a little bit more. As you can see, there is a force between the moon and the Earth that's pulling the gravity to the moon, and it goes both directions. Now, the interesting thing is that there's always this connection between Earth and moon, because again, there's this gravitational pull. So even the Earth is sort of pulled over, which creates a high tide on the following end too. The low tides, again, are going to be 6 hours later.
A tragic scene. Entire cities flooded, entire towns inundated, an unending stream of floating debris. Buildings, cars, people swept away in an unstoppable wave. It's a brutal reminder tsunamis are dangerous and unpredictable. But what causes these giant waves and what can be done to minimize their impact? Tsunamis can strike with little warning because they're usually triggered by a sudden displacement of ocean water, like volcanic eruptions, landslides, meteorites, or, the most common culprit, earthquakes. In the deep ocean, a typical tsunami wave is barely noticeable and poses little threat. But the waves can spread out thousands of miles, rolling across the ocean at speeds up to 600 miles per hour. As the rolling water reaches the shoreline, the wave's friction against the shallower floor slows it down and raises its height. By the time it reaches the shore, the wave can be as tall as 100 feet. Unlike ordinary waves, a tsunami wave doesn't crest and break. Instead, it moves forward like a solid wall of water that crashes over the coastline, obliterating almost everything in its path. And just when you think the danger is over, it recedes, dragging everything back to the ocean. Tsunamis have multiple waves which can continue to hit the shore for several hours, causing even more destruction. The word tsunami originates from Japan, a country that sits on a geographic location that makes it an easy target for these natural disasters. In 2011, it was struck by a tsunami that claimed nearly 16,000 lives. But the deadliest tsunami in history is believed to be the Indian Ocean tsunami of 2004. The U.S. Geological Survey estimated that tsunami released the energy equivalent of 23,000 Hiroshima-type atomic bombs. An earthquake created an estimated 600-mile rupture on the ocean floor. This caused the tsunami to form and then travel at the speed of a jetliner, reaching over 11 countries, traveling over 3,000 miles, killing more than 220,000 people. Because they can strike so quickly with such deadly force, tsunami warning centers around the globe are on constant alert, monitoring underwater earthquakes large enough to trigger massive waves. Their ultimate goal is to alert vulnerable coastlines and give residents time to seek higher ground before a tsunami hits.
And that's the end of our notes for today. Hopefully you were able to get everything down. Remember that you will be not only assessed on the information that we learned today on currents, waves, and tides, but also with the reading that you did and the questions that you answered on tsunamis for your Unit 2 quiz. Don't forget to submit everything on Maxis. Have a great day.